Now I got the unit normal vector over here, so I'll just erase this and I'll just calculate the first derivative of the unit binomial vector. Okay, ds d over here, and this is equals to, doing the calculation very quick, minus bc squared, okay, and then n squared. Sorry, n written in terms of s, the arc length. Okay, you can just simply differentiate this one. Okay, then later you can sneak in. Okay, I like to say sneak in, or that's not a proper term, but really find the minus cos CSI, take away sine CSJ. Why don't I just write it in full form so you can see what is going on? Okay, it actually turned out to be like this. Okay, BC sine CSI, okay, plus BC squared. So this is squared cos. Oh, sorry, this is a cos. This is sine. Okay, cos here, sine here. Okay, there we go. Okay, and then I can immediately see that when I introduce a minus sign inside, these two become negative, such like the ones over here, and then I can extract out the BC squared or minus BC squared, and that will give me this over here. So what I do is that I find the binomial vector over here by this equation over here. Unit tangent crossed with unit normal to find the binomial vector, okay? After that, I will differentiate the binomial vector with respect to s to get this thing over here, because I know that the formula requires the first derivative of the unit binomial vector, okay? And then later I can write the first derivative in terms of the unit normal vector, which I also need to find over here, okay? But the unit normal vector I find by finding kappa, and I find the unit tangent vector, okay? So I really hope that this example really shows the sequence in thinking, okay? You need to be clear on the sequences in thinking. So this is what we get over here, and torsion, okay, is equals to BC squared. Okay, the minus is already taken care of, and that is equals to torsion over here. And there we go. Okay, is there anything else? No, because we already got the unit binomial, the unit normal, and the unit tangent. Okay, and we already got kappa, which is over here, and we got the torsion over here. Okay, so what would this mean to our circular helix? Well, I can't really show you using calculus, but I can tell you, not good yet. Okay, the circular helix. Okay, let's just draw this over here like that. Okay, and we can already say, or we can already show that the circular helix goes around this equation over here. Sorry, a squared. The shape goes like this. Okay. Okay, where the radius of the circle is a. Okay, there's the reason why it's called circular helix, because that's why it always goes in circle. Okay, but what we are concerned with is this value over here, this torsion value that we've been talking about. Okay, as a recap, I would say again that torsion is equals to the rate of change of the binomial vector with respect to change in the arc length. And knowing that the binomial vector is, we get the binomial vector from the unit normal and the unit tangent, okay, it suggests how the free net frame twists and turns. Okay, so when torsion is positive and when torsion is negative, okay, it will really give us the, I'm not sure what's the proper term for it, but let's just say right-handed or left-handed, okay? Similar to the right-handed basis and the left-handed basis, which I talked about earlier. Okay, so notice that torsion here is a constant, so the thing twists in the same direction all the time. Okay, now if it's more than 0, it's called right-handed, and how the thing twists is similar to how when you grab the coil, because the reason why it's a circular helix is really easy to see the illustration. When you grab it, it will travel in the direction of your thumb. Okay, if you grab it with your right hand. So now I'm going to grab it like this, okay, and then if the thing is going this way, so it should go upwards like that. So that would mean that if I grab it like this, the values go like that. So, okay, there's a bit wrong here because I draw it wrong if you notice, okay, okay, let's do that again. Okay, I grab it with my right hand over here, so the cord is going this way and it's going up, okay, so it will need to go twist this way. Okay, yeah, that's more like it. It's twisting this way, okay, and it's going up. So the arrow to point the direction is like that. Okay, and now I hope you can see it better. Okay, on the web page I use Photoshop to make the picture, so I think it's a much better representation. But that's right-handed. So you grab it with the right hand is the direction of where the cord is turning or where the cord is going up. So in this case it's going up here like that. Okay, from the Freenet frame. So one way of using torsion, just like how we really covered a lot of ways on what curvature represents, is really finding the direction of twisting and which direction the curve is going given certain conditions. Okay, in this condition over here is when torsion is equal to a constant. Okay, remember these two are constants, so this is how we go. The circular helix, finding out kappa, finding out torsion, finding out the unit, binomial, normal and tangent, and interpreting what torsion means. Okay, bear in mind that perhaps the main thing over here is this one over here, which I would like to highlight again, is that the first derivative of the unit binomial vector in terms of S is equals to minus torsion, the unit normal vector, and that is how we find torsion over here. Okay, bit of hard work, but so I'm also getting a bit tired, but at least we got something covered today. Circular helix. Go, hope you liked it.